Can lasers solve one of the biggest problems in 3D printing? If you want to mark a 3D printed part, you have a few options. You can use a pen, but that is usually the worst idea because the extrusion lines act like tiny capillary channels and quickly pull the ink away from where you actually want it. So instead of clean lines, you often just get a blurry mess. You can, of course, multicolor print, and with the right printer, the right slicer settings, and a bit of patience, you can get incredible results. But the resolution is usually still limited by your nozzle size, and depending on the part, it can take a lot of time, material swaps, tuning, and also not look great. Stickers are also an option, but they often don't look very professional, and on 3D printed surfaces, they don't stick very well either. In professional applications, there is UV printing, which can produce absolutely beautiful results directly on printed parts. But it is still a comparatively slow process, and the machines are only now starting to come down into a price range where smaller workshops might consider them. But there's another option that has become much more approachable in recent years: laser engraving and laser marking. So for today's video, I haven't only printed and laser marked dozens of samples, but we'll also go over the different laser types, technologies and the mechanisms, so you can finally understand the differences and can find the right one for your job. Let's find out more. Guten Tag everybody, I'm Stefan and welcome to CNC Kitchen. If you look closely at many of the products you buy these days, especially tools, electronics, mechanical parts or injection molded components, you'll notice that the markings are often not printed in a traditional sense. They are laser marked, and that makes a lot of sense. Lasers are toolless, fast, and they allow every single part to be customized individually. Serial numbers, QR codes, part numbers, logo, Etsy shop personalization, or even just a clean label on a prototype can be added without making a stencil, a stamp or a screen. But the laser world can be pretty confusing because there are so many terms: diode, CO2, fiber, MOPA, Q-switch, neodymium YAG, ytterbium YAG, blue, green, red, UV, infrared, pulse, continuous, and so many more. I've had quite a few lasers over the years, from old Cartesian diode machines to CO2 lasers. But every time I saw one of these extremely satisfying coin cleaning videos with a fiber laser, I got that little tickly feeling that I seriously want to play around with also something like that myself. So I was very excited when xtool reached out and asked whether they could sponsor a video and provide one of their machines. xtool is one of the well-known companies in the semi-professional laser market. What I find interesting about them is that they don't build machines for laser experts. They also target people that want to use a laser as an actual tool, with polished hardware, laser safety and software that does not require you to become a laser processing engineer before you can engrave your first part. Marius, who shares the studio with me, had one of their metal fabs for a while now, and I think at this point he basically doesn't do anything else anymore except design parts that can be laser cut and welded. So I was pretty confident that xtool would be a good partner for this topic. My original plan was to use xtool's F2 Ultra, which combines a 60 watt MOPA fiber laser with a 40 watt blue diode laser. And honestly, this whole laser marking 3D prints video was at least partly an excuse to finally make my own coin cleaning footage. And I have to say, yes, that really works. But when I pitched the 3D printing angle to xtool, they said that I should also try their new F2 Ultra UV laser because that machine is supposed to be especially good at marking delicate materials, including plastics. And I was honestly very happy that I was able to get my hands on this machine as well, because it really makes a difference. Cleanly marking 3D prints can actually be surprisingly challenging. And if you want to make professional looking and individualized parts, multicolor printing often simply doesn't really cut it. We recently had exactly this problem here in the studio. My colleague Robin wanted to label his SMD component magazine. They are 3D printed and normal ink printing just didn't work properly. The ink got pulled along the layer lines by capillary forces and smeared across the surface. Currently he's using UV printing and the results look really nice, but the process is also pretty slow. That motivated me to find out whether lasers could be a faster and more economical solution. Spoiler, yes they can, but as always it depends. Lasers are light, typically focused down to a tiny spot, and to give you an idea of why they are so powerful and can even instantly evaporate metals, I did a bit of napkin math. Probably everyone has already used a magnifying glass to burn something, and you know how intense and bright that spot can already be. So my 90mm magnifying glass focuses the 1000 watts per square meter that you can have on a sunny summer day down to a 2mm focus spot. This increases the power density. So how much energy hits a specific area? In this case, it's 2000 times, and you get to roughly 200 watts per square centimeter. With the two lasers that I've tested, the numbers become really insane. Even though they are only 5 and 60 watts in power, the focus spot is much smaller, 30 and 10 micrometers to be precise. At this scale, if you would run them continuously, the power density in the laser spot is 42,000 or 31,000 times higher than with your magnifying lens. But since both MOPA and UV are pulsed lasers, which amplifies the peak power, to which we'll also get later, the MOPA peak power in the spot during a typical power pulse is more than 3 million times higher than the bright spot your magnifying lens can produce, and this explains why you can easily and instantly vaporize metals or even stones with it, and also cause some other interesting effects we'll see in a bit. So let that quickly sink in. When those high intensity lasers reach the plastic that we want to investigate, different things can happen, and this is not only a result of the polymer, but also the additives and colorants that were used, and sometimes the latter is even more important. So before I started testing, I printed a large variety of test plates from different materials and in many different colors, so that I could later engrave them and compare the results. But before we jump into the test pieces, we need to quickly talk about the different laser types, because not every laser is good at the same job. And the reason is not just power, it is a combination of motion system, wavelength, beam quality, and whether the laser is continuous or pulsed. If you understand that, it becomes much easier to understand why one laser burns a plastic part into a molten mess, while another laser creates a clean, high contrast marking on the same material. Let's start with the motion system, or in other words, how the laser spot moves over the workpiece. Most inexpensive diode lasers and many CO2 cutters use a gantry system, which is basically similar to a 3D printer. The laser head, or at least the focusing optics, physically moves over the workpiece. This has some big advantages. You can build large working areas relatively simply, and this is therefore great for cutting sheet materials. Another important advantage is that gantry systems can also easily carry additional hardware directly at the tool head, like air assist. Air assist blows air into the cut, removes smoke and debris, reduces flare-ups, and usually gives a much cleaner cut. The downside though is speed. Even if the system is well built, you are still moving a lot of hardware around, and that limits accelerations and engraving speed. Then there are galvo scanners. A galvo system uses two tiny rotating mirrors to steer the laser beam over your workpiece. These mirrors sit above your working area before the focusing optics, are lightweight, and therefore can move the laser spot very quickly. We are easily talking about speeds that are an order of magnitude higher than the typical gantry machine. And the precision is also excellent and easily below 0.01 millimeters. That makes galvo systems ideal for fast engraving and marking, especially for things like serial numbers, QR codes, logos, and small detailed graphics. The trade-off is that the working area is usually smaller, unless you combine the system with a conveyor belt or another positioning stage. A galvo scanner also has to solve a very interesting optical problem. If you just used a normal lens, the beam would be in focus only at one distance to the lens. But as the mirrors scan the beam away from the center, the distance to the workpiece changes and the focus would no longer lie on a flat plane. Instead, it would form something like a curved bowl. This is why galvo systems usually use an f-theta lens. This lens helps keep the focused spot more or less constant over a flat working area, even though the beam hits the lens at different angles. And I think that is pretty cool, and you should know about that. Now let's talk about the actual laser sources. The most common entry-level lasers are diode lasers. These days they're usually blue and around 450 nanometers. At low power, a module may use just a single laser diode, while higher power modules combine the output of several diodes using beam combining optics to reach, for example, the 40 watts of the xtool F2 Ultra. Generally, they are compact, relatively affordable, and can work on many organic materials like wood, cardboard, leather, some plastics, dark acrylic, and at high powers, even metals. But they also have limitations. Since the wavelength is visible blue light, clear materials often just let it pass through. That's why a blue diode laser is usually not the right tool for cutting or engraving clear acrylic. Beam quality can also be an issue, because the raw beam from a laser diode is usually not a nice round spot. Depending on the optics and how multiple diodes are combined, the focus spot can up elongated or rectangular rather than a clean round dot, which affects how finely you can engrave or how cleanly you can cut. CO2 lasers work very differently. They typically emit light at around 10,600 nanometers, deep in the infrared. This wavelength is absorbed very well by many nonmetals, especially wood, leather, paper, rubber and acrylic, including clear acrylic. So if your main job is cutting or engraving large non-metallic sheet materials, a CO2 laser is usually the way to go. It is fast, powerful, scalable and also very established. Then we get to fiber lasers, which usually work at around 1064 nanometers. This wavelength is much better suited for metals and used a lot in industrial marking, cutting and welding applications. And this is also where many of those satisfying coin cleaning and rust removal videos come from. The new and interesting option for me in this video was the UV laser. A typical UV laser works around 355 nanometers, so on the other side of the visible spectrum compared to the infrared fiber laser. This shorter wavelength has two big advantages. First, it can be focused to a very small spot, which is great for fine details. Second, UV photons carry much more energy per photon than infrared ones, and many materials, including plastics, metal and even glass, absorb UV light much more strongly than longer wavelengths. UV marking is sometimes called cold marking. That does not mean that there is no heat at all, but the interaction works differently from longer wavelength lasers. Because the absorption is so strong, the energy is deposited in a very thin surface layer, and because the pulses are extremely short, the surrounding material has very little time to heat up. To test this, I even managed to engrave my logo into the head of a match without lighting it on fire during the engraving process. That took a bit of trial and error, but I was honestly surprised how well it worked in the end. So in a way, a UV laser is more like a tiny surgical knife. It is usually not the right tool for fast cutting or deep engraving, but for high resolution, low heat, high contrast markings on delicate materials, it can be extremely useful. And don't get me wrong, you have seen that even though it is only 5 watts in power, the power density due to the small spot is ridiculous, and it even works flawlessly on metals. We did our own tests with copper, and there are other guys using the xtool Ultra UV for prototyping PCBs, for example, and basically do ultra-fine insulation milling with it. And now there's one more very important difference that took me a while to really understand and appreciate. Continuous versus pulsed lasers. Most diode lasers and many semi-professional CO2 cutter lasers emit something that is more or less a continuous beam. While cutting, the beam is basically on all of the time. So a 40 watt diode laser delivers around 40 watts continuously into the cut. That is useful when you want to keep heating, melting or vaporizing material a longer tool path. Fiber marking lasers and UV marking lasers usually work differently. They are typically pulsed lasers. Instead of being on continuously, they fire extreme short bursts of energy. So if a pulsed laser has an average power of, let's say, 60 watts for the F2 Ultra, the power during each individual pulse can be thousands or even 10,000 of watts. You can think of it like a reservoir that gets charged up and then dumped in an instant. And you need to distinguish this from the PWM mode that you have on a diode laser, for example, which is used to control the power output or to burn in grayscale images. Quickly turning on and off a continuous laser lowers the average power and does not have the same effect as on a real pulsed laser, because the maximum power stays the same. Just like a light bulb, you only turn it on and off very quickly. One of the settings you can often adjust is the frequency, so how many pulses the laser fires per second. A lower frequency means fewer pulses per second, but each pulse can carry more energy. A higher frequency means more pulses, but each individual pulse contains less energy. This is one of the reasons why pulsed lasers are so effective for marking. They can create extremely intense microevents on the surface of a material. Depending on the material, that can cause ablation, oxidation, discoloration, foaming, carbonization or texture changes without necessarily melting the whole part as much as a continuous beam would. And this also brings us to the MOPA laser. A MOPA laser is usually still a 10,064 nanometer fiber laser, but compared to a simple Q-switched fiber laser, it gives you much more control and more precise control over the pulse parameters, especially pulse duration and frequency. That means you can tune even better how much energy is dumped into your pulse surface in a given time, and therefore tune how much it is heated. This extra control is what makes MOPA lasers especially useful for things like color markings on stainless steel, where you can tune the oxide layer on the surface and therefore the color that you can see. And with this background, it becomes much easier to understand why some laser technologies work well on plastics and others don't. You can absolutely mark plastics and other materials with a diode or a CO2 laser, but it is often a very delicate balance between doing nothing, melting the surface, or burning the part. And if you constantly work with different materials and colors, it can become frustrating very quickly. So as I said earlier, I printed test samples in more than a dozen colors and several different materials, including PLA, PETG, TPU, ABS, and polycarbonate, to find out how well they mark and how easily the process is to set up. The xtool machines use xtool Studio, which is their own software for creating projects and tuning settings for materials. And since every material and every color can react differently, the software has a built-in test pattern generator. You can choose two parameters, set a lower and an upper limit, and the software generates a grid of parameter combinations. That is exactly what you want for this kind of testing, because with laser marking, the correct setting can vary quite a bit depending on the material and color. I first played around with the settings to get a feeling for the range. The F2 Ultra goes up to 15,000 mm per second in speed, but with the UV laser I noticed that the most interesting changes happened in the lower third of that range. So for most of my test plates I used the range from 10 to 100% of the 5 watt laser power and 250 to 4,500 mm a second travel speed. On many materials, that gave me a very useful gradient. In one corner, the energy input was so high that the material melted, charred, and sometimes even burned. Then there was a band where I got a clean, high contrast mark, and in the opposite corner, the energy input sometimes was so low or the speed so high that barely anything happened anymore. Before we look at all of the results, two quick things. How lasers actually mark plastic. There are usually a few different effects involved: discoloration, pigment change, foaming, carbonization, and material removal. A dark material can turn lighter if the laser creates tiny bubbles on the surface, because those bubbles scatter the light. Think of it like how the bubbles in your bathtub look white and are not transparent. A light material can turn dark if it carbonizes or if the pigment changes. And depending on the laser and setting, you can also remove pigments, roughen the surface, melt the polymer, or even ablate material away. Keep this in the back of your mind as we go through the results, because the same laser can create a mark by completely different mechanisms depending on the material and color. Second, a quick word about safety. You have already seen a lot of shots of the laser in action with the enclosure not fully closed. I only did this so I could properly film the process. And you have to jump through some hoops before the xtool machine even allows you to run like that. But please don't take this lightly. With a blue laser you can see the beam and you immediately understand that it is bright and dangerous. With the UV and MOPA laser, the actual laser light is outside the visible spectrum. If you see something, this is only the plasma or the glow from the interaction of the laser with the material. But the invisible laser radiation itself can still be horribly dangerous. And you only have one pair of eyes. So if you work with machines like this, make sure you have the proper safety equipment, the correct laser safety glasses for the wavelength you're working with, and use the enclosure whenever possible. When a laser interacts with a plastic, it can create smoke, particles, and potentially nasty decomposition products. xtool sent me their Safety Pro air purifier, which worked really well for my setup, and you should never run these machines without a proper filter or directly venting outside. If you think smoking is bad, laser fumes from random plastics or metal condensates are not exactly something you want in your lungs either. Alright, but now let's go through the lasers one by one. The UV laser ended up being the star of this test. It worked on the widest range of materials, required the least amount of tuning, and on most samples I could simply run a broad parameter grid and find a useful marking somewhere inside of it. Under the microscope, the UV marked samples were fascinating. If I didn't go overboard with the energy input, the material usually didn't look burned or charred like a wood engraving. The surface often stayed surprisingly intact, and the contrast seems to come from a combination of microfoaming and changes or removal of the pigment. Some colors like blue turned almost white in the marked areas. The only material I really had problems with were the red samples and some of the dark carbon fiber materials. That brings me to one of the most important lessons for this whole project. The marking quality often depends more on the pigments and the additives than on the base polymer. Most of my samples were PLA, but I also got very similar results on PETG, ASA, TPU and polycarbonate. The marking result was driven much more by the color and pigment system than by which polymer it was, at least on the UV laser. Though there were still some material differences. Some plastics foamed more easily, others changed color without much surface texture, and sometimes the filament manufacturer even made all of the difference. The clearest example of this was the white PLA. The white voxel PLA gave me probably the most impressive results of the whole test. The contrast was unlike any of the other samples and it marked beautifully dark, but the Bamboo Lab white PLA behaved much worse. Similar color, also PLA, but completely different results. This is exactly why you cannot just say white PLA works or white PLA doesn't work. The pigment and the additives can make a ton of difference. The UV laser is also outside the visible spectrum, so materials that look transparent to our eyes are not necessarily transparent at 355 nanometers. That's why I even got visible results on the transparent samples. The contrast wasn't as strong as on the opaque materials, but the laser definitely interacted with the surface. One more thing I noticed under the microscope, and this is a bit of a tangent here, but I think it is very interesting. The engraving often wasn't a continuously filled area. It consisted out of many tiny dots, which really show the pulsed nature of the laser. But the dots were closer together near the edges of the engraved areas and more spread out in the middle. This happens because even though the galvo mirrors are very lightweight, they still have to accelerate and decelerate. Near the ends of each hatch line, the scanning speeds are lower, so the pulses land closer together. In the middle, the lasers are moving faster, so the same pulse frequency creates a larger spacing. From my time working in metal additive manufacturing, where we also used a laser that was steered by a galvo scanner to melt metal powder, I know a technique called skywriting. The idea is to extend the motion path beyond the actual marked area, so the laser only turns on once the scanner is already at constant speed inside the part and turns off again before decelerating. That gives you a much more uniform energy input. I'm honestly curious why something like this isn't implemented here. For most practical markings, it's probably not a huge issue, but under the microscope you can definitely see it, and also sometimes with your bare eyes. The perceived contrast also depends on the dot density. Some areas look lower contrast simply because not all of the base material has been touched. If you run the laser slower, at a second pass, or increase the line density, more of the surface is affected. That can be a problem if you want to make a solid marking. But it can also be a feature. By changing the settings, you can effectively engrave different shades rather than only a light or dark mark. After the UV tests, I repeated many of the same tests with the 60 watt MOPA laser. The results were a bit more mixed. The first thing I noticed is that 60 watts of average output power is often simply too much for plastics. Instead of testing up all the way to 100% power, I reduced the maximum to around 30% for many of the samples. The F2 Ultra MOPA is simply much more at home on metals, where you actually need that power cushion. On some materials and colors, the MOPA worked very well, and you could clearly see that the pigment was being destroyed or changed, creating a lighter mark. On other samples, it was harder to find a clear process window. The MOPA does give you more parameters to play around with, especially pulse frequency and pulse duration, and those settings can absolutely help you tune the results. I didn't optimize every single sample in details, because that would have turned into a 12-hour video, but I did adjust the settings on selected samples to understand what was going on. One interesting thing I saw under the microscope, on some MOPA marked samples, darker hue samples had larger dark char particles underneath the surface, in contrast to the UV marked samples, which were uniformly darker. So even when both lasers created a visible mark, they don't necessarily create it by exactly the same mechanism. Finally, I tested a 40 watt blue diode laser that is also built into the F2 Ultra. For a clean plastic marking, the results were a bit disappointing. Probably because of its more continuous nature and also because of its wavelength, it often just puts too much heat into the material. Many samples either showed almost no useful contrast or quickly turned into a melted plastic pool. That doesn't mean the blue laser is useless. It's excellent for many jobs, especially cutting and engraving materials that absorb the blue light well, and where you want the charring. But for clean, high contrast markings on 3D printed plastics, it's simply not well suited. That said, the fact that the lasers can melt plastics, sometimes even quite evenly, gave me a different idea. A year or so ago, I saw a video by Minwin 3D where they attempted to laser smooth a 3D printed part, and the results looked very impressive. That might not only have visual applications. If you locally remelt the layer lines, you might also improve the strength in these areas. I mean, each of the 3 lasers was able to melt the plastic to some extent, and the interesting question would be, which one allows you to do this the most controlled way? If that's a future video you'd like to see, let me know. And after all of this testing, let's circle back to my original challenge, Robin's SMD magazines. The goal was to find out whether we could mark them faster and more economically with a laser instead of UV printing them. So I printed a sample plate from the same light gray Bambu Lab PLA that Robin is currently using for his magazines. And of course, because this is how testing always works, that exact color gave me one of the worst contrasts of all of the samples, especially with the UV laser. The MOPA laser actually performed a bit better here, which was uncommon compared to most of the other materials. Looking closely at the other samples, many UV laser markings had a slightly gray hue, which is more or less the base color of the filament. So there simply wasn't much contrast to create. But I didn't want to give up. I refined the settings around the parameters that gave me the best contrast on the initial broad test. That further improved the results. With the UV laser, I still couldn't find a setting that produced a good contrast without damaging the base polymer. So in the end, I actually settled on a setting where the surface melted slightly and also charred a bit. With the chosen settings, I engraved 2 actual SMD magazines. The UV marked one had a darker engraving. It actually didn't look too bad because the shiny molten surface added some additional contrast. The MOPA marked one was lighter and looked a bit more defined. Both were acceptable, but neither looked as good as the UV printed reference. Out of curiosity, I also printed 2 magazines in black PLA and engraved those. And there, especially with the UV laser, the results looked amazing. The marked area turned almost white and had very high contrast. And that really summarizes the whole topic. Most materials seem to be markable if you tune the parameters, but the effect can be brutally different. And sometimes the best solution is not to keep fighting the laser settings. Sometimes it is smarter to change the filament color or even just the filament supplier. MOPA and UV can work, though the UV laser was easier to get right in my tests. Laser marking is used a ton in injection molded parts, and there are even special laser marking additives. You can add them in small quantities to a plastic, similar to a color master batch, and they make the material much easier to laser mark. Depending on the additive and the polymer, they can help create light marks on dark material through foaming and create dark marks on light material through carbonization. A friend gave me an injection molded lid that contained such an additive, and the engraving quality and contrast was superb. That made me wonder whether there might be an interesting application for special laser marking 3D printing filament. Or maybe it is just simpler to test existing filaments and find the ones who work already well. But a marking is only useful if it lasts, so I wanted to get a feeling whether the color change was permanent or just some temporary smoke residue sitting on the surface. I cleaned some of the samples with isopropyl alcohol, and the only thing I was really able to remove was a bit of smoke and soot that had stuck to the surface. The actual marking stayed very durable. Even scratching did not remove much of the contrast, though you sometimes see some scratches. That was a very encouraging result, because that suggests that the marking is not just simply sitting on the surface. It is actually a change in or near the material surface itself. So what else did I do with the machine? I marked and engraved a few things around the studio and at home, especially parts where I previously would have used a label marker or simply not had any marking at all. But one application I was especially proud of, and which really shows the amount of details you can get with the UV laser, are these tiny bracelet beads I made for my daughter. I printed the beads themselves from plain PLA, only a few millimeters wide. Then I made a simple fixture that holds the beads in a repeatable position and locates them against a stop inside of the machine. After that, I simply used a setting that had given me the best contrast on the matching sample and engraved different tiny images on the beads. The results were honestly really impressive. At that scale, the small spot size and the precision of the UV laser really shines. For me, the whole project was a very interesting learning experience. Not only have I now a much better understanding of how different laser types work and which ones are suitable for which job, but I now also have tools in the studio that I will definitely use for future projects and prototypes. I put all of my test samples on a ring, so whenever I want to mark something in the future, I can quickly check which material and color might work before spending hours printing samples and then guessing settings. And what is my practical takeaway? For marking 3D printed plastics, the UV laser was the easiest and most reliable tool. It worked on the widest range of materials, required the least amount of tuning, and usually produced the cleanest results with the least amount of thermal damage. The MOPA laser was also very capable, and on some materials it worked even better than the UV laser, but it is clearly more a metal marking machine. And for plastics, the 60-watt version often has way more power than you really need. The big advantage though is the extra control over pulse duration and frequency, which gives you more ways to tune the interaction. The blue diode laser was the least useful for cleanly marking plastics in my test. It can mark or melt some plastics, but the process window was much narrower, and it often produced heat damage before it produced a nice high contrast mark. And the most important lesson, filament color and pigment chemistry also matters a lot. Two materials that are both white PLA can behave completely differently. So if you want to laser mark your printed parts reliably, testing your exact filament is absolutely necessary. Working with the xtool machines has been a real pleasure. The hardware feels solid, the machines are polished, and the software is intuitive enough that you can get useful results very quickly. Especially with the built-in generators and the community projects, I can absolutely see these machines being useful for small shops, Etsy sellers, makers, and prototyping labs that want to make customized products without becoming laser experts first. The one thing I am still missing is proper light burn support, because that would give me even more control over the surface and the tool paths. Especially after seeing the dot spacing behavior under the microscope, I would love to have deeper access to the scanning strategy. Anyway, thanks again to xtool for sponsoring this video and providing the machines. If you're looking for an approachable laser solution from CO2 to fiber and UV lasers, check them out using the link below. Thanks for watching everyone. I hope you found this video interesting. If you want to support my work, head over to Patreon or become a YouTube member. Also check out the other videos in my library. I hope to see you in the next one. Auf Wiedersehen and goodbye.